Hi there, my name is Rachel Kurchin. I'm a postdoc at Carnegie Mellon University, and I'm really excited to spend a few minutes today talking to you about my new package, ElectrochemicalKinetics.jl, and what we can do with it. If you'd like to get in touch with me, there's a few ways shown at the bottom of the screen here, and I'm also happy to answer questions on the conference channel Discord. I assume that will be Discord again. So this is obviously not a science conference, but this is a very science-oriented package. I'll try to keep the technical details to a minimum. And the main thing important to understand here is what is electrochemistry? Electrochemistry is chemistry plus electrons. So here's a diagram from Wikipedia on different types of chemical reactions. And the important thing with electrochemistry is that some of these species are charged. Some of them are electrons, some of them might be charged ions. And because of this net electrical charge, the electrical potential becomes a really powerful control knob for these reactions. And so what I'm specifically interested in is modeling the rate of those reactions as a function of the electrical potential that we apply. So shown here is a very simple redox reaction, reduction oxidation between metallic lithium and a lithium ion plus an electron. So note that the overall charge is always balanced. It's neutral on both sides. But on one side, we have these charged species that we can impact with an electrical potential. So the core question in electrochemical rate modeling is how do the reaction rates forward and reverse of this reaction, and hence the current flowing, because again, when we have charged species moving around and exchanging, there's an associated electrical current, depend upon the voltage we apply to drive it. And I've chosen lithium here as a very sort of illustrative and suggestive example. Electrochemistry is extremely important in energy storage via batteries and other important energy technologies as well, such as electrochemical capacitors, electrocatalysis for chemical synthesis, and a variety of other processes. And so you might want to understand here, for example, if you want to charge your electric car very quickly, how much potential can we apply to drive the reaction at a given rate, or vice versa. If we apply some potential, how fast will the battery charge? How much current will flow? And so in general, we'd express this as some reaction rate constant or an associated current as a function of that overpotential, which we often denote as eta, and some set of parameters that we're using to model this process. And within the package, this looks like this. So we have a function called rate constant, which takes in a value, which takes in a parameter eta, as well as some kinetic model object that describes these different models. And the package is really based around this function. And then one other function that we build as sort of an inverse to this function. So you can imagine if you have some rate constant and some model, you want to know what overpotential would it take to drive that rate constant. But generally, these expressions for the rate constant as a function of overpotential, they're analytic, but they don't necessarily have analytic inverses. So we can invert this via a numerical solve, and that's accelerated by some of the great automatic differentiation capabilities we have in Julia. So we have access to these gradients. We can do this via gradient-based optimization quite efficiently. There's a number of different models available. So there's a few very conventional ones that a lot of electrochemists would have heard of, such as the Butler-Volmer model or the Marcus theory, as well as some more sophisticated ones, such as the Marcus-Hush-Chidsey model, and a variant of it that I introduced a couple of years ago that incorporates the density of states, or the DOS, of the electrode. And some of these models require computation of an integral. And so they have a different subclass of this kinetic model as compared to Butler-Volmer and Marcus, for example, that don't require computation of an integral in order to evaluate the forward rate constant. So what are the capabilities of this package? Well, of course, we can compare the predictions of various models. So we can construct these different models and predict the current as a function of overpotential and make what's called a Tafel plot here. So the log of the net current flowing as a function of the overpotential that we apply, either positive or negative. We can fit models to experimental data. So this is actually a figure from the paper where we introduced this MHC plus DOS model. And we can also easily implement additional models. So some collaborators in my group, along with experimental collaborators of theirs, developed a improved version or an adapted version of this MHC plus DOS model, where they incorporated effects of quantum capacitance, which turns out to be really important when we're thinking about electrochemistry at interfaces with two-dimensional materials like graphene. Another thing that I've been working on more recently is electrochemical phase diagrams. So in a thermodynamics contest, if you've taken a thermodynamics class, you're probably familiar with the relation that the chemical potential is the derivative of the Gibbs free energy with respect to particle number, and that this relation can be used to build phase diagrams. So if we have, for example, a thermodynamic model that shows separation into two phases at certain compositions X, we can build the phase diagram by understanding the sort of trade-offs in energies as we go to different temperatures or different pressures or other thermodynamic conditions, and understand at what compositions, at what thermodynamic conditions we will see that phase separation versus when we'll see uniform mixing. And the idea of these electrochemical phase diagrams is to add current on as a dimension of these phase diagrams. And we can do that by adapting this chemical potential term to be some thermodynamic model. So in these cases, I've used a very simple ideal solution model and adding a term that depends upon the current that's flowing. And this takes advantage of that inverse function that tells us the overpotential as a function of current here. And we add a term that looks like this onto the conventional thermodynamic model. And we can then build these phase diagrams that has here composition on the x-axis. So we can imagine how much lithium has intercalated into some electrode for a battery, for instance, and see what that phase separation behavior will look like as a function of the model that we use. And we see that we can get really qualitatively different behavior. And I'll note that this is a linear scaled current here, while this is a logarithmic scaled one on the left. And so the same value of the current where we see this different phase separation, oh, the cat has joined the talk here, shows up at these locations here. And so the interesting thing here from a scientific perspective is that you see, roughly this 2x difference between these two models, and that it happens at a current before the Tafel plot on the left here really shows much obvious separation between these models. So that's pretty interesting in and of itself. And of course, because this is all automated and quite efficient within the Julia package, we can do these multi-dimensional phase diagrams, which are quite interesting. So now we have a conventional thermodynamic variable of the temperature on one axis, and then the composition and the current as well. And we see, again, these quite dramatically different shapes depending on which electrochemical model we use, and we're able to investigate this very easily now. So that's all I have. Thank you so much for your attention. I'd like to give thanks especially to Daria Gandhi, adjunct wizard. So a lot of the automatic differentiation capabilities that underlie the functionality in this package would not have happened without his help, and I'm very grateful for that. My advisor, Venkat Viswanathan, and members of the group, especially those who have used the package or contributed to it. JuliaCon organizers, thank you for running what I'm sure will be an absolutely amazing conference. And of course, you all for your attention. Thank you so much. Fred says goodbye too.